This will be the first of 3 videos on AC circuits. So this is the chapter where it all comes together, where we need to know a little bit about everything for this chapter. We're generalizing what we did with circuits before. So before we would have a DC battery, so always providing current in a single direction, direct current, EMF source, and then we put different circuit elements here. So we've seen resistors, we've seen capacitors, we've seen inductors connected, and a few different combinations of that. In this chapter, we're replacing the DC source with an AC source. So this is the way we depict it. We have a circle with a sort of a sinusoidal shape right here. So we're going to see a lot of sines and cosines here. And that's sort of the shape that we have in the middle of that circle. That just like a sine wave, a little tilde thing. This is representing an AC source. So an AC source has a voltage across it that is sinusoidal in time. So if we look at the voltage of the source over time, it doesn't matter whether it's like a sine or a cosine. So we're going to be talking about things that are common for all times. So a lot of times we don't really care about the phase constant. But the fact that it's switching is important, and the fact that it's sinusoidal will be important. So there's some maximum EMF of the source, E naught for the source. But a half a period later, it's going to be the polarity is going to be reversed. So what's plus and minus will be reversed. So it keeps swapping back and forth. So this video, we're going to look at replacing this with 3 different circuit elements. So we're going to look at an AC source connected across a resistor. We're going to look at it connected across a capacitor, and we're going to look at it connected across an inductor. And then the next video will complicate this a little bit. We'll see what happens when we actually do all 3 at the same time. So a resistor, a capacitor, and an inductor all at once. So this will be a series RLC circuit. But for this video, we'll keep it relatively simple. So we'll just keep one circuit element there. So the point is to systematically build up how we're going to analyze these circuits using something called phasors. So that's the first thing we're going to go over. And then we'll go over each of those 3 things. All right, so a phasor is a mathematical representation of a sinusoidal function. So really what we're talking about here is voltages and currents. For every one of these circuit elements, the voltage and the current is going to be sinusoidal, a sinusoidal function of time. So it has a graph that looks like this when you plot it versus t. But there's a different way of representing that will be nice, that will be handy for us. And that is in terms of a phasor diagram. So that's what this thing is right here. So these 2 things are representing the same information. So what a phasor sounds really complicated. All it means is a arrow that's rotating in space. So this arrow is rotating counterclockwise. So notice how there's this direction of just symbolizing like that this thing is rotating in time this way. So it looks like right here at t equals 0. At t equals 0, the thing had peak EMF. So that means that this phasor started out right here. This was where the phasor was at t equals 0. So the way we read this graph is you take the tip of the arrow. So the base of the arrow is always at the origin. You take the tip of the arrow and then you project it onto the horizontal. And that's the value of your function at that time. So after a quarter of a period, for example, this phasor is going to be pointing up. So this is the phasor at 1/4 of a period, right? 1/4 of the amount of time it takes to go all the way around the circle. If you take the tip of that arrow and you project it down to the horizontal axis, you get 0, right? You get the x, like horizontal component is equal to 0. And that corresponds to this right here. That means the value, the instantaneous value of the, looks like we're plotting a voltage here. The instantaneous value of the voltage is 0. A half a period after the start, it looks like the value is the negative peak EMF. Okay, so again, just saying the same information as what's in this graph, but visually a little bit different. So this is called a phasor diagram, and it's always going to be rotating counterclockwise in this plane. Right? Your book tries to avoid complex numbers as much as possible. Really, what this plane here is the imaginary part of a complexified. So you can talk about voltages as complex numbers, and this is the imaginary part and the real part. Your book is trying not to scare you with complex numbers. So really, we'll get away with not talking about complex numbers. If you're electrical engineering, ECE, something like that, you're going to be talking about this a lot. So you'll talk about complex impedance in your ECE classes. I'll let you discover that fun later in life. Okay, so like this stop and think right here. So this is the phasor right here. And notice the phasor is constant in magnitude. So the length of this arrow is constant over time. It's just rotating in place. So a short while later, it's going to look like this. It's going to rotate, and the projection on the horizontal is going to be a little bit more negative. So that means that at this moment, the magnitude is actually increasing, right? Because it was right here, and then it was right here. So you're getting farther away from the origin. So the magnitude of the voltage is increasing at this moment, all the way up until the phasor gets to this position. That's when it's max in like the negative direction. All right. Okay, so that's phasors. So we'll be drawing phasor diagrams, and we'll see how they get more complicated later. Okay, so our first circuit is a AC circuit with a resistor connected to it. Resistors are the easiest of the three objects: resistor, capacitor, and inductor. Resistors are the easiest because everything happens absolutely instantaneously. There's no time lag or anything associated with this. So in other words, if you apply like 10 volts across a resistor, then immediately, instantaneously, basically, there will be a current that goes from the higher potential side to the lower potential side. And the amount of the current is determined by Ohm's law. So you have V across the resistor is equal to IR, I across the resistor times the resistance of the resistor. And because of Ohm's law, because R is constant, this is directly proportional to this. And so when this is a max, this is a max. When the voltage is zero, the current is instantaneously zero at that instant. When the voltage is in the other direction and maximal, then the current is in the other direction and maximal. They're just going with each other. They're going in the same direction. By the same direction, I mean when one is a maximum value, the other is a maximum value, and they're in phase is the point here. So the graphs look like this, them being in phase. The voltage across the resistor and the current through the resistor are in phase. In terms of our phasor diagram, the two phasors are, because they're in phase, they rotate together. They're with each other. They're not like at some angle relative to each other. You might wonder, like, how quickly are these things? Well, you're probably not wondering it, but I'm asking you to wonder about how quickly are these phasors rotating around in this plane? Well, the answer to that is the angular frequency of whatever is driving this thing. So the source has angular frequency, omega, which is the number of radians per second. In the US, in the wall outlet, it's 60 hertz, 60 cycles per second. So the voltage swaps back and forth. So it's positive and then it becomes negative and then positive 60 times every second. That's a lot. So in the US, the 60 hertz, if you turn that into what omega is, this is radians per second. There's 2 pi radians for every cycle. So this would be 120 pi radians per second. So if we're ever talking about a problem where you're plugging something into a wall outlet, this is the value of omega. This is pretty big, right? This is like close to 400 radians per second. So this is the value that goes here. And this is also telling you how quickly these vectors are spinning around. They're going very, very fast, right? 400 radians per second, that's a lot of revolutions per second. 60, it's going around in a circle 60 times per second. So when we're drawing these plots, we're drawing, someone took a picture at, one instant in time. At that instant in time, these two are lined up with each other. Notice how they're both zero at the exact same time. So current and voltage are both zero at the exact same time. when you're plotting two phasors on the same diagram, notice how these have completely different units. This is amps and these are volts. And so the arrows of these things, if you're comparing like volts and current, the arrows, the length of the arrows mean absolutely nothing relative to each other. So in other words, whoever drew this, they could have drawn the current phasor longer than the voltage phasor, and it wouldn't have mattered. Like they're setting a different scale, you know, a scale for the voltage and a scale for the current. So don't read into that too much. Now, if we drew this voltage phasor and then we drew another voltage phasor for another circuit element, then you would have to like pay attention to the size of this versus the size of this. If you're drawing like voltages and currents on the same thing, you have to pay attention. And that's why they did use different colors right here to try and focus your attention differently. Okay. And that's the point behind this stop and think as well. Okay, so the other two are a little more complicated, the capacitor and the inductor. So as a sneak peek, notice how the two things aren't in phase here at all. So the voltage across the capacitor and the current that's going through the capacitor. By through the capacitor, we have in mind that, you know, the capacitor actually has like a gap, you know, some insulation between the two. So current is just collecting on one plate and simultaneously leaving the other plate. So that's what we mean when we're talking about current through the capacitor. Notice how these two are not in phase. So the reason for this is that the voltage across the capacitor, if you remember CV equals Q, and if they're time varying, your book is using the convention that they're doing lowercase here for the time varying things. So the voltage depends on the charge collected on the capacitor, but the current is related to the time derivative of the charge. So the current and the voltage, so the current and the charge, or the current and the voltage are off by 90 degrees because when you take a derivative of either sine or cosine with respect to time, you get the other one, right? Derivative of sine is cosine, derivative of cosine is minus sine. So you get a trig function that's 90 degrees out of phase, one way or the other. Whether this current vector is this way or this side relative to the voltage, they're 90 degrees apart from each other because of this derivative relationship between the two. So real quick, I'm gonna jump ahead to the, we'll come back to the capacitor, but I wanna contrast this. So I want you to notice that the current is in front of the voltage. Right? We say that the current leads the voltage in a capacitor. So I'll talk about why that is in just a second, or I'll give you a hint for how to think about that. So the current's in front. Notice how both these arrows are rotating. So they're both rotating at the same angular frequency because it's determined by the source. So the source is driving everything in the circuit. It's driving the frequency around it. You know, these things are rotating around with that frequency. Whenever the current is here, the voltage is right here. So the current reaches some max. And it's a quarter of a period later that the voltage becomes max. So the voltage is lagging behind, the voltage phasor is lagging behind the current phasor, or the current leads the voltage for a capacitor. In an inductor, so we're gonna skip this section until the next video. In an inductor, it's exactly the opposite. The voltage phasor leads the current phasor. So which one is in front depends on what circuit element you have. And for a resistor, they're in phase. So you can already jump ahead and look at this example problem that we have. You can maybe guess which of the two circuit elements it is, but it's definitely not a resistor because they're not in phase. Right? See how they're 90 degrees out of phase? So the hint for why this might be, or the way I remember this, is that it's sort of a cause and effect relationship. So whatever comes first is the cause, and then this is the effect. Right? So in a capacitor, you start with a capacitor that nothing interesting is going on. There's no charge on it or anything. What has to happen first is that a current needs to be delivered to the plates first. And then after that, a voltage builds up across the plates of the capacitor. So the current is what happens first, and then the voltage lags behind. because the current needs some time to accumulate charge on the capacitor's plates. So the current leads the voltage in that case. For an inductor, where's this thing? Here. For an inductor, the cause is a voltage. So you try and force current through an inductor. So you zap it with a battery. So the voltage comes first, and the inductor doesn't like that. It has a back EMF. It really doesn't want to drive current, but eventually it relents and it allows current to go through it. It can't prevent it forever. But the voltage comes first. That's the cause. The voltage happens first, and then eventually you can get current to go through the inductor. So the voltage leads the current phasor by 90 degrees in this case. And again, this has to do with the derivative relationship very explicitly for an inductor, because the voltage across an inductor involves the derivative of the current. Remember that, just when we talked about inductors and inductance. The only thing that I've sort of glossed over here, well, one thing I've glossed over, is this thing called reactants. Reactants is sort of a generalization of resistance. We'll see what I mean by that in just a second. Generalization of resistance. So remember that, okay, so for a resistor, the voltage across a resistor is equal to the current across the resistor times the resistance of the resistor R. So we like Ohm's law, and we try and basically force it upon other things. We like it so much that we want to say, so whatever this value is, there's some maximum value of current in this circuit. By this circuit, I mean the AC source with the capacitor. There's some maximum amount of current, and there's some maximum amount of voltage, right? It's the magnitude of these two phasors. And so what we write is we want a relationship between the two that looks a lot like Ohm's law, V equals IR, except we can't call it a resistance for a capacitor. A capacitor doesn't follow Ohm's law. We can't call it a resistance. We already said that we're going to define a resistor to satisfy it to be an ohmic device. So we can't call this a resistance. So we just call it X. So we use the letter X for this, and it has units of resistance. So X is measured in ohms, because if this is volts and this is amps, this is definitely ohms. But it's called a reactance. And there's an X sub C for capacitive reactance, and there's an X sub L for inductive reactance. X sub C is this right here. And so that I don't have to scroll down a bunch, the X sub L is omega times L. So it turns out that these have units of ohms. So omega is 1/seconds, radians per second are 1/seconds, and then C is in farads. So if you took 1/seconds times farads, and then you took the reciprocal of that, turns out you get ohms. And if you had 1/seconds times henries, turns out you get ohms. So what's interesting here is that the omega, the frequency, is on the denominator for this one, and it's on the numerator for this one, for the inductive reactance. So let's try and think about why that is, okay? So let's suppose we fix the overall voltage. So if you just have a simple circuit element like this, the V sub C, or if we replace this with a inductor right here, then it would be V sub L, would just be equal to the voltage of the source. So again, in your wall outlet in the US, it's like 120 volts. Really, if you actually took a voltmeter, it's maybe more like 115 volts, 120 volts. And that would be the magnitude of this voltage phasor right here. So if you hooked up your capacitor to a wall outlet, then your capacitive voltage phasor would be that amount, 120 volts. Okay, so let's fix that value right here. And then let's explore this as a function of frequency. So imagine you could play with the frequency. Like really 60 hertz for your wall outlet, you can't really play with. But imagine you had a knob that you could turn up or down the frequency. A capacitor, imagine you had a really low frequency. So every year you flip directions. very, very low frequency, right? Once every year. So really long period means a really short frequency. What happens then is that it's so long, like a whole year. What happens is that it basically looks like a DC source, right? If it takes a whole year to flip, you can basically replace it with a battery for a few months and it looks very similar. If you have a DC source, then the charge accumulates in a certain direction on the capacitor, and that just stays there, right? If this is a constant voltage, if this is always the plus side and this is always the minus side, then this is going to fill up with plus charge, minus charge, and it's going to stay there. And so you sort of saturate the capacitor, and you don't get any current in the circuit. So in other words, as omega goes to 0, the current dies down to 0. So if the current dies down to 0, that means the reactance is infinitely big, okay? And this sort of makes sense why omega would be on the bottom, right? And actually, the faster that you flip the two, the more the capacitor just acts like a short, just acts like a wire, because it's flipping so fast that it doesn't have enough time to accumulate charge. And if it doesn't have enough time to accumulate charge, it doesn't care. Like you can put as much current as you want through it. It doesn't matter. Like it doesn't build up charge to resist, to prevent the current from going in the circuit. An inductor, though, acts very opposite to this. So an inductor really does care about how quickly you're trying to change the direction. Because remember, the magnetic induction, it matters how quickly you're changing the magnetic flux. So if you're trying to reverse the direction of the current, you're going to get a really, really big back EMF, or really big effective resistance, which we're calling this thing reactance. So the bigger the frequency, the bigger the reactance for an inductor. But the bigger the frequency, the lower the reactance for a capacitor. Okay, so this thing reactance is like a generalization of resistance. It has units of ohms, but it's frequency dependent for these two circuit elements. Whereas for a resistor, it's not, it's independent of frequency. It's just the resistance of the resistor. I believe that is everything for now. More to do next time, but that's it for those three circuit elements. So let's look at this example problem then. So in this problem, it looks like the voltage leads the current. So stop and think about, which circuit element was this? Was this an inductor or a capacitor, where the voltage comes first, and then because of that cause, the effect is some current going through the device? So it leads the current by 90 degrees. So not only does it lead it, but it leads it by that particular phase. So what this means is that we have an inductor. It's the inductor for which you have to apply a voltage difference, and then it'll eventually, you can get current to go through it. So we have an inductor. So we know that this is going to be the coil circuit element. It's ugly. Coil. There we go. Okay, so it's an inductor. And we want to describe what's going on in the circuit at the instant shown. So at the instant shown, which is this, this is showing a particular time. So this is some particular T star, call it. So at this particular instant, the voltage is maybe the opposite of what we would expect. So the plus, so this is maximal EMF across that the source is providing. And that means also, from a Kirchhoff loop rule, that we can say that this is the plus side and this is the minus side for the inductor. So despite that, there's actually zero current going on in the circuit at this instant. Because remember, you take the tip of this arrow and you project it down onto the horizontal. And it looks like we get 0. So the current was just positive. The current was going this way. So T just before. At T just before, the current was this way. And just after this moment, it's going to be going the other way. But at this moment, it's actually just frozen. There happens to be no current. And notice how what's going on here is that the voltage, so if this is at higher potential than this one, well, okay, so this EMF source is trying to have current go around this way. But the inductor doesn't like that, and it's preventing that from happening. But eventually it sort of relents, and current can go around in the circuit in the counterclockwise direction. So in a moment just after this, current will be going in the counterclockwise direction. So here in this phasor, it looks like that current phasor is going to become non-zero because it gets a little bit, apparently that's negative for this phasor. And also this starts to decrease in voltage across those two terminals, right? Like right now it's a maximum and then it's going to decrease in magnitude a short instant later. Okay, more next video.